Welcome to the final part of the introduction into design of reinforced concrete structures. In this part, we're going to discuss the durability and fire resistance of concrete. We'll start with durability and the importance of concrete cover for reinforcing steel. The aim of design for durability is to ensure that a structure is serviceable throughout its lifetime. The durability of reinforced concrete structures is influenced by several factors, and they include exposure conditions, cement type, concrete mix and quality, cover to the reinforcement, width of any cracks, and construction procedures. All these factors are interdependent. Let's discuss them in a bit more detail. The exposure conditions depend on what factors a certain face of a structure is exposed to. It can be atmosphere, soil, seawater, de-icing salts, chemicals, etc. One face of a structure can be exposed to several different factors. For example, part of an offshore structure is submerged, another part is in the splash zone, and the third part above the splash zone. All these three parts of the structure will be in different exposure situations. The exposure conditions govern the type of concrete mix and the minimum cover to the reinforcing steel. The type of cement to be used in concrete structures will depend on the exposure conditions. For example, if the structure is going to be exposed to chemical attacks, blast furnace and sulfate-resistant cements will be used. Since the hydration reaction is exothermic, that is, it releases heat, low-heat cements are required for massive sections to prevent cracking of concrete due to thermal expansion. When construction time should be minimized, rapid hardening cements are used to produce concretes with high early strength. The exposure conditions influence the choice of concrete mix and quality. Concrete mix is defined in terms of minimum cement content, maximum free water/cement ratio, lowest concrete strength class, cement type, aggregate size, and air entrainment. In reinforced concrete structures, steel bars are embedded in concrete sections. Concrete between the surface of the structure and the surface of the bar is called cover. Concrete cover is essential for protecting the steel against corrosion and fire, and for safe transfer of bond forces. The thickness of the cover depends on exposure conditions, concrete mix, and quality, as well as on the intended design life of a structure. Eurocode 2 distinguishes chemical and physical environmental conditions, which are classified based on EN 206-1. The classification depends on the following factors: risk of corrosion, type of aggregate agents, which can be CO2 or chlorides, freeze-thaw attack, and chemical attack. All names of exposure classes start with two capital letters. The second letter represents the factor causing the structural deterioration. 4 out of 6 exposure classes are relevant to reinforcement, and they include XO, XC, XD, and XS. XO is the most favourable exposure class, and it represents a situation where there's no risk of corrosion or attack. XC is the exposure class with a risk of carbonation-induced corrosion, and the other two exposure classes are related to the risk of chloride-induced corrosion and depend on the source of the chlorides. XD represents the risk of chloride-induced corrosion, where the chlorides are coming from sources other than seawater, de-icing salt being the main source. And XS represents the risk of chloride-induced corrosion, where the chlorides are coming from seawater. The two other exposure classes, XF and XA, are relevant to the deterioration of concrete, and they account for the risk of freeze-thaw attack and chemical attack. Table 4.1 in Eurocode 2 provides descriptions and examples of corresponding environments. As mentioned earlier, different parts of one structure can be exposed to different environments. Examples of different environments with corresponding combinations of exposure classes are shown in this picture. One of the main parameters in the design of reinforced concrete structures is cover. Cover is defined as the distance between the concrete surface and the closest reinforcement surface. This distance includes links and stirrups and surface reinforcement where relevant. In the picture on the right, you can see examples of concrete cover. Nominal cover is calculated as the sum of the minimum cover, C-min, and the allowance of deviation, delta C-dev. During concreting, reinforcing bars should stay in certain positions within the envelope of a structural element, as can be seen from the bottom pictures. Spacers are used to keep reinforcing bars in place. Spacers have different forms depending on the intended use. Examples of spacers are shown in the pictures to the right. Spacers can be made of concrete or plastic. Metal spacers are not used because they corrode and can cause corrosion of reinforcing bars. Here you can see several examples of the application of spacers in construction. Spacers can sometimes be spotted on surfaces of reinforced concrete structures. Here you can see spacers protruding in some of these surfaces. There is a large variety of spacers. Here you can see many examples. The allowance for deviation is required to account for possible mistakes in positioning or reinforcement leading to a decrease of concrete cover. Examples of such mistakes include the use of smaller spacers or large step of spacers leading to excessive sagging of reinforcing bars. A typical value for the allowance for deviation, delta C dev, is 10 mm. This value can be decreased to 5 when a quality assurance system is applied, including measuring the cover thickness. The allowance for deviation can be reduced even further when an advanced measuring system is used and non-conforming parts are rejected. As discussed before, minimum cover is required for safe transmission of bond forces, as well as for protection against corrosion and fire. These factors are taken into account in this expression for the minimum cover. Here, C-min-B is required for adequate bond, and C-min-dur is required for durability reasons. The other delta C durabilities given in this equation are corrections for the minimum cover for durability depending on specific conditions and materials used. The value of the minimum cover cannot be smaller than 10 mm. The adequacy of the cover for fire resistance will be discussed later on in this lecture. The minimum cover for bond is taken as the diameter of the bar or an equivalent diameter of a bundle of bars for which the cover is calculated. The minimum cover for durability depends on the exposure and structural class. Table 4.4n in Eurocode 2 defines the minimum cover for durability. For example, a structure of class S4, which is exposed to the environmental condition XC2, should have a minimum durability cover of 25 mm. The structural class is defined in table NA21 in the National Annex to Eurocode 0 as a category for design working life. Typically, reinforced concrete buildings are designed for at least 50 years of service, which corresponds to structural class S4. Structural class can be modified according to table 4.3n, depending on several criteria, including the design working life, class of concrete, geometry, and type of quality control. Table NA1 in the UK National Annex to Eurocode 2 sets all the corrections for the minimum cover for durability that we saw in the previous slides as equal to 0. One of the environmental conditions relevant for concrete is XF, that considers risk of freeze-thaw attack. In this table, strength class of concrete are defined for several severities of this type of exposure, depending on whether air entrainment admixtures are used. Since porosity is an important factor that limits the effect of freeze-thaw on concrete, the water-cement ratio is kept high in the case where no air entrainment agents are added. As we discussed before, the concrete cover also protects the reinforcing steel from elevated temperatures caused by fire. Fire results in a dramatic increase in temperature of structures. Mechanical properties of concrete, and especially steel, are affected by high temperatures. In these diagrams, you can see the detrimental effect of high temperature on strength and stiffness of these materials. Structural fire design is based on satisfying several conditions for a defined period of exposure to fire. These conditions include structural strength and integrity, and heat insulating performance. The heat insulating performance depends on the flame penetration resistance and heat transmission properties of a structural material. The heat insulating performance depends on the flame penetration resistance and heat transmission properties of structural materials considered. Concrete has relatively low heat transmission properties. This means that the reinforcing bars will have lower temperature when they're located deeper in the concrete section. Lower temperature of the steel bars means that the reinforced concrete structure will be able to withstand fire for longer. The diagram on the right shows the distribution of temperature within concrete at different durations of exposure to fire. As can be seen, temperature decreases very quickly with increasing concrete depth. Concrete cover for fire is defined as the distance A from the main reinforcing bar axis to the nearest exposed concrete surface. As a result, the concrete cover for fire is different from the nominal concrete cover considered earlier. In design, both covers are calculated. The distance from the concrete surface to the surface of the first bar is calculated from the concrete cover for fire and compared with the nominal cover. The largest value should be provided. When the reinforcing concrete bars are stacked, that is, positioned in layers, the concrete cover for fire is calculated as the distance from the nearest exposed concrete surface to the centre of gravity of the stacked bars using the following formula. The concrete cover for fire is defined based on the condition that design effect of actions in the fire situation is smaller than the design load bearing capacity of a structural element in the fire situation. The concrete cover for fire is provided in tabulated form in Eurocode 2, Part 1.2 for different structural elements. It should be noted that the nominal cover provided by the durability requirements often governs the design. In the next few slides, we will look at the tabulated data for concrete cover for fire given for few different structural elements. Tables 5.2a and 5.2b in Eurocode 2, Part 1.2 contain data on concrete cover for fire for columns with circular and rectangular cross-sections. Table 5.4 in the same Eurocode contains data on minimum dimensions and concrete cover for fire for walls. Tables 5.5 and 5.6 contain data on minimum dimensions and concrete cover for fire for simply supported and for continuous beams with different cross-sections. Tables 5.8 and 5.9 in Eurocode 2, Part 1.2 contain data on minimum dimensions and concrete cover for fire for simply supported one-way and two-way solid slabs and flat slabs. And tables 5.10 and 5.11 in Eurocode 2, Part 1.2 contain data on minimum dimensions and concrete cover for fire for simply supported two-way solid ribbed slabs. And that brings us to the end of our introduction into reinforced concrete design. We've discussed the material properties of concrete, reinforced concrete, the Eurocodes, and also fire and durability. In the next couple of lectures, we will start designing structural elements, mainly beams, flanged beams.